it's a great honor and pleasure for me to be here. And I would like to talk a bit about AI failures. So what to do if AI is going wrong and what to do about it. Whereby it will not really address the real challenges which have been highlighted by Katharina and Professor Seeberg, Professor Morik a moment ago, like the ethics, the biases, but already technical challenges are a problem, basically. And why is it so? All models are wrong. This is from a famous statistician, and of course machine learning models and AI models, being statistical models, are wrong as well. For example, in such a simple two-class classification, I have to get accustomed to this one, is it? So here you see that, of course, there's no reason if you train on the data points to have the decision boundary exactly like the underlying one. Partially you can see that on the training set already, but partially you might observe this only during running the model, like here, this tiny difference directly at the border, where you have these adversarial examples. For example, in this case, the 3D printed turtle, which just from every angle looks like a gun, but never like a turtle for a deep network. Or these areas where you have no observations before, like this big red fire engine, which was not observed by the autopilot from Tesla. So these are incidences how errors appear in practice. The problem is not that they are errors, but the problem is that they are not accounted for and they are very unexpected. This is one of my favorite examples showing that models can be completely wrong and useless in practice. Here, an intelligent camera should focus on the ball in a soccer game. And I'm not sure you see the ball. Actually, the camera does a really good job based on the mistake that the ball is the bald head of the referee, which is really nice. But it's a funny game, basically, if you're not interested in the game itself. And that's an example of that humans do not necessarily understand why AI is wrong, because you would say, come on, this is not a ball. So people need to understand that here AI is mistaking because it is based on vision only and no other common sense reasoning. The model assumes it is 100% correct and never hesitating to focus on this really nice ball. And then if an error occurs like here, the humans cannot do anything about it. So they will probably always wear hats from now on at these soccer games. But that's the only solution which is there for them. And I would like to have a little bit of a spotlight into what one can do about it, whereby these are very tiny aspects, a very small part of the research going on, and which is still to do. So for making AI models understandable, of course, you can go for XAI methodologies, and I would like to have a glimpse into a specific one. To equip AI models with a notion of them not being correct, you can go for what would be called reject options. And if an error occurs, humans want to change this, you need what would be called lifelong learning. And I would like to delve into these three aspects in a little bit of the time I have. So let's start with XAI, which refers to every possibility to equip a machine learning or AI model with something a human can understand, either directly because it's a natively interpretable model, or after training to equip a black box model with some type of insight. There do exist many methods. There will be a session on XAI, so many people in the centers on the French as well as the German side are working on that, and some of the, in my opinion, best textbooks at the moment comes from Munich. Some of the best methods come from either causal learning or Berlin, like the LPR. So there are many different methods around which can be distributed into which language do they use. So there are the feature-based approaches like the LIME. There are methods which deal with natural language explanations, which you can see on the upper right. There are prototype-based methods, either natively or on top of deep learning models. And there is also visualization to have a scatter plot for a deep network, also for high dimensions to see how the decision boundaries would look like. Apart from the modality you use, you can distribute or distinguish the approaches according to whether they are local or global and how they compute the explanation. And I'm not going into all these increasingly, exponentially increasing approaches, but I would like to go into a specific one, counterfactuals, and tell a bit about what is still open for counterfactuals, how they can be and how they can be used, how they are beneficial. Counterfactuals, this one, are an instance of a post hoc in its vanilla form black box, example-based and local explanation method. They come from psychology, and more or less in this case, in that setup, a counterfactual would explain for a selected data point what the data point would have to change to be on the other side of the decision boundary. And this explanation is a minimum one, so it aims for a minimum change to explain why are you here and not there. And of course, this is an optimization problem, which can be phrased, for example, like shown here. So what is open here? The problem is if you phrase it as such an optimization problem and you deal with black box optimization technologies, you might often have problems because you might have no unique solution, which is called the Rashomon effect, and it might take quite a while. So you can do research, for example, on how to phrase counterfactual explanations as a convex optimization problem, and this is possible for models such as the prototype-based ones, which would yield such a set of optimization objectives which are convex. And for many other models, it is possible to phrase this actually as an efficient form if you go model-wise. If you want to check it out, go for this QR code where you have the counterfactual explanation toolbox developed by Andre Artelt in my group. Another challenge is that counterfactuals are not necessarily what a person would expect to have. Let us show for the nice old MNIST data set. So this is a 6. And now I ask the question, I don't want to be a 6. What do I have to do to look like a 3? Then a counterfactual explanation for a decision tree model would give you this one. Oh, make a blob here. Where you would say, come on, that's not a 3. And similar for the other ones. The problem is these data are extremely high dimensional, so counterfactuals in this, actually, if you take them directly, would become counterfactuals. So you have tiny, non-realistic changes and not plausible explanations. So what you might want to do is you might want to equip your optimization problem with some notion of plausibility, such that the explanation having a certain minimum probability of being observable based on estimators, probability estimators of the data. And that, in this case, would lead to different explanations, not this one with this blob, but the 6 should be more like that to be a 3. The 9 should be more like that to be a 0, and so on, with a nice side effect that these explanations are also much less dependent on the model you use. So actually you get the same here, independent of whether you look at a decision tree or a support vector machine, and you can prove that if you have large margin cases, so to speak. I would like to go into one application. So where are counterfactuals useful? This is part of a synergy grant called Water Futures, where we want to solve SDG 6, drinking water for everyone. Of course, we will not solve it, but we can go for tiny problems, such as short-term control of water distribution systems, where a sub-problem is to detect leakages or faults and to detect, for example, sensor faults. Let's go for this sub-problem, how to detect sensor faults in water distribution systems. This is L-Town. It's a benchmark example of a city, so the pipes in a city, very similar to Limassol, but of course pipes of cities are not open. But there do exist mock-ups scenarios with physical simulations which are pretty good to play around with that. Here you have sensors, pressure sensors, and what you would like to detect is whether one of these sensors is faulty, and if so, which one. And we want to do that with explainable AI, so counterfactuals. What we can do is we can go for what would be called a residual-based fault detection approach, meaning we build models for every data point here. So for every location of a sensor, we build a model where these values are predicted based on the others, and we take a threshold if there occurs an error, and such a threshold method would lead to a pretty high sensitivity to detect the faults. Now we would like to locate which sensor is the one which is faulty, so we would like to say, okay, it is this one. For that we can go for a counterfactual explanation, because what we want to know is which sensor to change such that everything is correct again. And this would be a counterfactual explanation pointing us to the point where the error occurred, so which is the cause of the error. We do this with not only having a counterfactual but a sparse one, such that one sensor is identified. The problem is this is wrong. It's not the sensor. And this is due to the fact that in such a setup, you have high correlations of the different nodes. So you have to do yet another plausibility regularization, so to speak, because you have to compute the counterfactual not for only one, but for all different sensors at once, which we called an ensemble consistent explanation, which would give such a profile pointing here to the true cause with 97% accuracy. So this is an example of actually a practical use of counterfactual explanations in a domain of high relevance in a technical domain. So, but do counterfactuals actually help humans? And if so, which ones? Because, of course, I started with the challenge to explain AI models to humans. To do that, we need user studies. So we have to really approach humans. And the question is, of course, do we go to water distribution system experts? We wanted to go to laypersons. And in order to be able to evaluate counterfactual explanations in a scenario everyone can understand, we designed the Alien Zoo. Which will pop up in a moment, I hope. So the Alien Zoo is a game where you have aliens, so the chaps, and you can feed them with 5 different types of leaves. Depending on how you feed them, they grow or they shrink. The challenge is to grow them as much as possible. The nice thing is that behind the dynamics of chaps growing actually is a machine learning model, which has been learned based on a very simple logic thing, taking a few data points. So it's not exactly this very simple logic thing, but it's a machine learning model, in this case a decision tree. And now we can investigate whether people are better off feeding chaps and understanding what are important feeding factors with or without explanations, and with one type of counterfactuals or the other, so plausible counterfactuals versus non-plausible ones. This would then look like that. So here this would be the setup without explanation. You just see how the chaps grow, and if you would have the, sorry, I have to go back. With the explanation, you would have such a setup where it is explained that you would have been better off if you would have used this number of leaves as compared to this one. And you repeat that, counting how much improvement you get over a number of cycles. One can now compare the condition with or without explanation. And it is a fact that if you use explanations, you are significantly better off than not using explanations. And also people are possible to better identify which of the features are relevant as compared to pure chance level. Pure chance would be 2.5. This one is actually, if you don't have explanations, people are even worse than pure chance. And what is interesting, you can also investigate which types of explanation to give. So we investigated if we give closest or plausible counterfactuals. And here again, you see a quite significant difference, which is actually unexpected for us, because here the closest were better than the plausible ones in the setup. And you can evaluate that so that you have a much better performance over the number of tries if you have the closest versus the plausible counterfactuals in the setup, which was a bit of a surprise for us. But you have no difference for the understanding. Both are significantly better than having random chance. So this is the first try to get into XAI and how this could help, on the one hand, technical systems, on the other hand, humans. So XAI is very important that there do exist many different technologies, but while these are useful in some technical domains and they are useful in some application domains, it's not really understood which methods to use for which setup. And another thing is that they are often extremely static, so it's very clear, which we have seen from this plausible versus the closest counterfactual, that usually you have to do some argumentation around and probably use a interactive scheme to really explain AI in its usage to a human. This is, among others, part of a newly established collaborative research center on explainability, which is a joint one between Paderborn University and Bielefeld. So I would like to go for the second topic, reject options. That is a challenge. If I have a model like that, can I equip the model such that points like that are just rejected, or points like that are just rejected, rather than doing a wrong classification? Mathematically, this would mean that we equip the classification prescription with a specific attribute, which would be the R for reject, which can be chosen whenever the model is insecure, and we can evaluate such a model using the extended 0-1 loss, where in case of reject we have a costs B, which are lower than doing a misclassification. So it costs, but not so much as doing things wrong. And this is important whenever there's a possibility to put a system into an interactive scheme where a human expert could help if it's in doubt, such as for medicine. In this scenario, it would, for example, be that all points here are accepted, and this one is not classified, and everything lying outside of the distribution of the data points would be not classified, but rejected to be classified. There do exist classical schemes to deal with reject options. Most are based on certainty measures. For example, if you have the likelihood or a confidence value or something like that, then you often have, in addition to your classification prescription, a confidence measure, which is a real number. And often you go for what would be called a reject strategy, which is threshold-based, where you just say, I reject whenever my confidence is lower than the threshold, and otherwise I classify. Is this a good choice? Well, there is very old work, already back to 1970 by Cho, which tells that if your certainty measure is the true probability, then it's the best you can do. You can rely on a global reject threshold, because this is probably optimizing your 0-1B loss. The problem in practice is that it's not working, because usually you don't have the certainty in a correct way. And I've shown you here an example from, this is AlexNet on the Cypher data set. And these are here adversarial data points. So this would be the 2D projection, so the scatter plot of what the network is doing here. And you see that this ship is classified as a car with 85% certainty. And here it's 100% sure this is a car. So you might have real problems if you rely on a certainty, because the certainty is usually not easy to estimate. Due to that, there do exist a big number of approaches how to, on the one hand, get better estimates, in particular for deep networks, of the certainty of the estimation. There do exist analytical approaches to go for surrogates. There do exist direct optimizations of the 0-1B loss or surrogates about that, even with supported by learning theoretic guarantees. You can learn reject strategies directly from data. There's this beautiful framework of conformal prediction. What I would like to delve in is one approach. What if we don't have a global threshold but local ones? And I would like to delve into that because it's an example of a classical problem of theoretical computer science popping up in machine learning, which I always find pretty nice. So we can rely on actually results from other domains here. Local thresholds must rely on a tessellation of the space. So you have to assume that your space is decomposed into different regions because, for example, you have a one versus rest support vector machine where you have always the SVM having the highest output as tessellating the space, or you might have a prototype-based model. So assume you have, like shown here, a tessellation in one region, the second, the third one. Then if you would go for global thresholds, you would pick, for example, for every of these regions, the second of these possible isobars for your confidence level. And if you would do so, you would have here, if it's a second one, 5 true reject, 8 false rejects. If you would go for a local threshold, so picking here the first, here the second, the third, you would improve because you would have more true rejects, less false rejects. So it might be worthwhile to go for that. Mathematically, it's the challenge to have a vector of thresholds, theta j, such that in the region J, you use this as a threshold, and the question is how to optimize those. You're aiming for the Pareto front of threshold vectors, maximizing true rejects, minimizing false rejects. It turns out this is a classical problem because you can just order the points according to their certainty. Then you have a fixed possible number in every region of possible thresholds. The overall true rejects are the sum of the true rejects per region. The overall sum of false rejects is the sum per region. And you end up with what would be called a multiple choice knapsack problem, where you choose from every region one of these possible thresholds, such as the gain, which is the true rejects, is maximized, while the loss, the false rejects, is minimized. So knapsack problem sounds bad because it's an NP-hard problem, but it's not strong NP-hard. And we are in the region here where we have polynomial time solutions. And we are even in a region where one can phrase a Bellman equation, like shown here. I don't go into details here. So you have a Bellman equation which can efficiently be solved with dynamic programming in polynomial time. Let me show you what this would yield, for example, in a medical application. This is a challenge to detect or classify adrenal carcinoma versus adenoma based on steroid markers in a medical domain, where of course you would like to have a high accuracy to get that correct. If you don't reject, you have 92% accuracy on a test set or in a cross-validation. Whereas if you reject a few of the data points, like 10%, for 10% you consult an expert, you end up with 95% or even 96% accuracy, so much better one, where you see that the local thresholds are a little bit but significantly better than having the global one. So let me conclude the second part. Reject options are a means to integrate that AI models can be wrong in a systematic way, and a huge variety of models exist. The problem is these are often not used, and the bigger problem is, of course, once the model rejects, like a car, I don't see what is going on, then what do you do, such that the system is running? So how do you treat this back, give it back to a human? Which is, I think, an open and very important research question. I would like to go to the third part. So once you have some understanding of an AI model, you know the AI model is wrong, what can you do as a human to change the system? And there is the necessity of having systems which can adapt after delivery to new data becomes absolutely relevant, which is continual or lifelong learning, an open research area which becomes more and more relevant. And of course, everything can go wrong once people can tweak models. Let me start with an application where it is shown that the possibility to adapt after the delivery might actually yield to much better performance. So this is an example from driver assistive systems. The idea is to have a crossing assistant where if you approach with a car and you want to turn right, a bike is right to you, you are warned, wait, the bike should go first, or similar on the left, or if you go straight. And what you have to solve as a subtask is based on driver behavior, detect or predict what the driver is going to do at the crossing. Here. This was a collaboration with a company producing manufacturing cars and motorcycles. And yeah, what you can do is you can, of course, detect or collect features. You use either here and here and here. You use either AutoML or do the tuning yourself, depending on whether you have good models available, like we've heard just a moment ago or not. And you end up with a classification prescription enabling you to initialize a warning if you turn right and there's a bike or not. The interesting thing is that, of course, you are better as concerns, you are better as concerns accuracy if you are closer to the crossing. So if you're 4 seconds before the crossing, you have twice as much error as if you are 1 second to the crossing. And the interesting thing is, if you train a model on all data you have gathered from all people, an average one, then you have a higher error as compared to if you let your model learn while the people are driving. So you can divide the error by a factor of 3, actually. So meaning lifelong learning would be very beneficial in this case to individualize a product after delivery. So how can lifelong learning happen? This is learning from data streams, where one would assume that we start with the model H0. We observe a data point and allow the model to adapt according to the data point. And this should happen all the while after the model is delivered. Why is this challenging? It is challenging because you might have what would be called change of distribution or drift. And you see here an example from a real data set from vision domain. This is Venice. And the task is to, you see here on the right, from a small region, which is taken here, the color histogram. The task is to predict which palazzo is this. So this would be, okay, I have this one, I could go here, which is another palazzo, another one. And you see very clearly that during the day, the color histogram changes a lot. So meaning this data point, which as a person you consider constant, is changing. It's a changing distribution. And this would be called drift, which might make a classifier trained at noon invalid if you use it at night. Mathematically, drift would refer to the fact that you have a distribution at time point t0 and probably a classifier or a model. Real drift means that the distribution changed in such a way that the original underlying classifier is no longer valid at time point t1, or it might happen that the classifier would still work, but the data points live no longer here on the lower left, but on the upper right, so which would be called virtual drift or covert shift. And you have to deal with it because that unexpected drift might happen. There do exist many methods to deal with drift, and there's a very popular toolbox from Paris, the River, from Albert Bielefeld and colleagues, where you have quite a number of methods being able to learn with drift. And we are very happy that one of the methods developed by us, the self-adjusting memory, is part of this French toolbox. This self-adjusting memory more or less is a parameter, non-parametric model, where we have come up with rules how to store and which data to store to build a non-parametric model based on that, whereby the storage happens in the term of a short-term memory relevant for the current setup and a long-term memory which stores everything which might be reused for the future. And instead of explaining this to you in detail, which is a bit lengthy, I show you how this model would set up the memories automatically if it is fed with a two-dimensional distribution which changes. So you have here 4 classes, black, green, red, blue, and they are moving from left to right. What you see here is the points the model saves in the short-term as well as long-term memory. I hope it will work. You see this as a video. And somehow it's very clear you have real drift here, so overwriting of old points and deleting of old points. You always here store what can still be reused. And altogether, these data points can then give the base for a non-parametric model, which is always optimum as concerns the point of time you want to deal with. You can make this even more complex by putting this memory model in an ensemble, which we did in a French-German collaboration 2 years ago. And then you end up with, having these beautiful tables machine learners always love. And of course, the message is like Professor Seebach just said, it works and we are the best, otherwise I wouldn't show this table. So the same would be this one, where on average we are ranked 1.6, and the same without the ensemble would be the next one. If you compare to adaptive random forest, leveraged gradient boosting, or very fast decision trees, you have a significant improvement for that. So you are able to learn after delivery. At that point, I was thinking about whether to go for mathematics or for humans. Because there's lots of mathematics which is not so clear. So what is drift? How is it related to non-stationary stochastic processes? Can we map it to dependence, independence? And that's possible, but I decided against mathematics because people are extremely important to be integrated into machine learning models. And what would be good if you adjust a model? Can you explain to a human, oh, this changed, so there's something to do about the model. Let me motivate why this might be a problem. Assume you have at time point t0 such a model with a decent accuracy of 96%, and now at time point later your model accuracy drops to a little bit more than 60%. Then it might be that you have very different setups which are causing this drop of accuracy. This one more or less is accounted for because data become more noisy. You have a new assistant doing the measurements not so correct as the previous one. Or it might happen that your data are actually moving. So the blue one moving to the upper part and the red one to the lower part. So here you would have to adjust the model. Here you would just have to tell your assistant to be more precise. And it would be good to have explanations if drift is observed, what is causing the drift, and how could that be translated into rules which point to relabel and how to retrain a classifier using a continual learning model. So we would like to have some highlighting of the drift regions, because here and here the data points are still okay. Here and here the data points are still okay. Here we have like a move of the data points from here to there. And here we have just this noise moving like salt and pepper. Can we come up with drift explanations? We can. And more or less this can, for example, be done with a 4-step approach. We can first detect when does drift occur. There do exist a number of drift detectors. Among others, we use the David, which was published by us. Then we need to localize regions of drift, which can be done based on what we call chomographies. We extract representatives for the drift regions, and then we use counterfactual explanations, to go back to where I started with, to explain why these points or these prototypes are before and not after the drift, which should highlight the changes in the data. And to show you an example, you can do this in parametric as well as non-parametric and unsupervised as well as non-supervised scenarios. This is a couple of examples of cute animals. So we use that for deep learning stuff. And other cute animals after the drift. So this is before, this is after the drift. And now I can ask you, where is the drift in these examples? If you do a drift explanation, you would be able to identify, pinpoint typical images which cause the drift and how they would look before and how they would look after the drift. We did that in a latent space of a GAN. Therefore, we could also come up with visualizations. And you see, the foxes are the problem. So the foxes actually are orange before and gray after the drift. So this would be before, this would be the same fox after the drift. Or here vice versa, this would be after the drift, and this should look like that before the drift. So you can explain that to a human, such that a human can directly delve into these characteristic regions and retrain a classifier using a lifelong learning model. One question is extremely unsolved. How can then laypersons teach machines, and how? We found this problem too big for us. And we delved into a very simple sub-problem. Can laypersons teach classification in 2 dimensions by selecting training examples? Which is an extremely unsolved problem. So is it possible for humans to really deal and teach the classical machine learning models? We started with here nearest neighbor, for example. This would be nearest neighbor. This would be the points which cause this nearest neighbor to happen in this way, or this would be decision tree with the points, and this would be the decision tree coming out. The question is, if we only give the coloring of the space, can a layperson place points such that we have roughly this tessellation of the space? This is calls again for user studies, and we did user studies where people were shown such a layout, and then they were allowed to place points in the regions which were labeled according to the color of the region. Here we have 3 points, so the first time there's a decision boundary taking place with a decision tree, and this can go on and on, and we can count after a number of rounds how much difference still persists. You see here, the person was not very successful because this whole region is wrong and this one. So it's a big error the people did here. You can do the same for a nearest neighbor, where people might come up with this tessellation approximating the underlying one. So you have this region wrong, this one, this one. And now you can evaluate whether people can do it better than chance and whether people improve over time, such that there's some chance to let people teach basic machine learning models. What came out is that both are better than random. So this is for decision trees, this is for random forests, so both are better than random, but improvement happens only for the nearest neighbor, not for the decision trees. It seems decision trees should not be taught by placing points by a human, whereas nearest neighbor might be an approach to do this way. If you compare both, you see that this is significantly better than the other one. So it's a first trial to evaluate in a very rough condition, can people, lay people having no idea about machine learning, teach that. And as an anecdote, it was so interesting for my oldest son that he wrote something like that himself. You can try it out. That's my son's code. He liked that so much to play around with it. So it might be some way to teach persons. Okay, so lifelong learning. To speak with Churchill, to improve is to change, but to be perfect, you really need to adjust the models after delivery. Powerful technologies exist, and also first approaches to get the human into a loop, but it is completely unsolved how to do this over a real full life cycle, which is one of the challenges we will address in a project which just started in the region where I live. Let me come to a conclusion with this nice question, does Bielefeld exist? For everyone who has never heard about the Bielefeld conspiracy, so Bielefeld is supposed to be the modern Atlantis. So everyone claims it is there, but no one was ever there. DFG places Bielefeld on its AI landscape somewhere here. You are welcome to check it out if you come close by. So once you are in Paderborn, Osnabrück, or also Dortmund, have a look whether we exist. We claim to have quite a number of nice projects like this collaborative research center on explainability. We claim to chair the North Rhine-Westphalian-wide AI graduate school on trustworthy AI, and we have quite a couple of networks on intelligent technical systems, which is in the region in Paderborn, Bielefeld, and the University of Applied Sciences, which is a technology network with more than 180 partners. And we are also happy that Bielefeld is currently chairing the cloud services and also the project of the German network of bioinformatics infrastructure. So it's a pretty cool area if you find it. It remains to thank my collaborators, which are, I didn't put all the pictures, but which are from my group as well as Germany and worldwide. In particular, I'm happy to have one French colleague on this list of things I could show to you. Thank you very much.
Thank you for your talk. We have 5 minutes for questions. Is there a first question?
Yeah, thank you very much for your talk. I have a question on your first part about the counterfactual examples. Can you discriminate or distinguish between counterfactual and adversarial example?
Yes. So the thing is, that's exactly what I've shown on this one example. So if you phrase counterfactuals in a plain way, it's exactly the same as you would phrase an optimization problem for adversarials. And that's a problem. In practice, if you have like lower dimensional data, you don't observe adversarials. If you go for higher dimensions, you often go for adversarials and don't get an explanation. Therefore, what is often included is what I call this plausibility constraint, meaning that you don't go just beyond the boundary, but you take into account the distribution of the data space and you go into the region where your data is natural, so that people would understand and observe this as a natural example and not a one which is just living somewhere in the data space but never observed in practice. And the question is, of course, how to do that on the one hand efficiently and on the other hand according to the problem in a precise way. For example, for the water systems, we had to take into account the whole network to get at that, which was sufficient here. Or you can, if you can do a density estimation, you can of course rely on a minimum density there. But it's one of these central questions. Thank you very much.
Can I add to this question? So you said it's enough to have examples that is close to the data manifold, right? And then it won't be this adversarial example. But then you can sort of have initial example, you have some constraint or regularization penalties that will force it to be close to this example, and if the model is non-robust, you can have an image that looks exactly the same as this image, so it's on the image manifold, but it's still not useful because it looks the same. So we need these robust models for this, right?
I'm not so sure so whether I got the question correct. So of course you are right because there do exist counterfactuals which are within the manifold. The counterfactual explanation does never look exactly the same like the, or it should not look the same like the initial one, because you go to the other side of the classification boundary, and then if you don't have examples which are adversarials in your training set, you wouldn't go there. So I'm not sure this was a question.
Yeah, sorry, I meant that there is this problem for non-robust models.
Yes.
That more or less, if you don't train it robustly, so that there is a ball around every data point.
Yes, sure. So the thing that you mean this adversary training to get robust models.
Yeah.
Yes, and of course, if you have a non-robust model, you would probably, if you explain why the model behaves this way, you would get funny results. But I would then claim that's exactly what you want to have, because you would have an explanation why the model is behaving the way it does. So you would not have anything which would be useful for human to understand according to what a human would observe here. If you would go for robust models, you would have counterfactual explanation which would be meaningful.
Yeah.
Yeah, and I would expect that to some extent, if you have non-robustness, you will have counterfactuals, because you can do the adversarials also with in the manifold and stuff like that. You would probably always have adversarials which are not useful for a human, but to understand the model scrap, which would do the job here, in my opinion.
Okay.
I'm not sure this is some compromise we might discuss later.
Okay, thank you.
Thank you very much for the question. It's a deep one, so I cannot answer in a short way.
Thank you a lot.
Okay, thanks for the nice presentation. I wondered whether you can also make sure that everything noteworthy is explained. I was wondering about this because the hamster was totally missing on your right-hand side, so I wondered whether it was eaten by the foxes or...
Yeah, actually, this was some random sampling, so thanks for pointing this out. Yes, you can, because what we do have is we have what we called identifiability function, where you can prove that if you do sufficient sampling, you identify all regions where actually a difference in distributions before and after exists. It's always a case of sampling in high dimensions, so here we went into the latent space of a GAN, where of course the latent space might be disrupted, but yes, theory tells if you spend enough resources, then we find everything up to regularization, blah, 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 stuff like that. In practice, no, of course, because theory is never valid.
Okay, the session is now over, so let's thank again our speaker.
Thank you very much.